In this video, we're going to talk about some of the uses of condition codes in the x86 ISA. Like so much about the x86, the complete story is really complicated, but we'll illustrate some of the more typical ways in which condition codes are used, specifically in flow of control operations like conditional branches. The x86 has a sizable set of condition codes, or flags, which are stored in the x86 state at fixed offsets within the E flags register. Each flag is effectively a 1-bit register. The value of 1 means that the condition is true, and 0 indicates that the condition is false. The x86 has operations that allow setting and clearing selected flags, storing specific flags, or pushing a subset of the flags onto the stack. We're only going to scratch the surface of what's possible within the rich x86 ISA. We'll consider only 3 of the many x86 flags. ZF is the 0 flag, SF the sign flag, and OF the overflow flag. The 0 flag is set to true if the most recent computation yielded a 0 result. If the sign flag is true, it means that the result was negative. And if the overflow flag is true, it means that the most recent computation resulted in a signed overflow. Check out the x86 documentation for the other flags and what they mean. Most often the flags are set by one instruction and referenced by a subsequent instruction, such as a conditional jump. Certain assembly operations set these flags, many do not. Notable among those that do are the arithmetic and logical instructions and the test and compare instructions. We'll look at each of these in turn. Let's first look at the setting of the condition codes with an arithmetic operation and how it might be used. Suppose that you've written a loop in C that counts down to 0. An example is shown here. This while loop decrements x in each iteration and terminates when x is less than or equal to 0. The assembly code that's generated for this by the compiler might be something like what's shown here. Here we assume that variable x is in register EDI. It's decremented by 1 on each iteration of the loop. A side effect of the subtraction instruction is the setting of the condition codes. As we've already explained, ZF is set to true if the result of the subtraction is 0. SF is set if the result is negative, and OF is set if the result caused an overflow. For our example code, a positive result means that we haven't yet reached the terminating condition of the loop. In that case, we jump back to label L6 and execute the loop body again. Otherwise, we fall through and continue executing in the remainder of the program. The JG, or jump greater instruction, implements this behavior. It tests the condition codes to see if they indicate that the result was positive and takes the jump if so. If not, we fall through and continue executing at the next statement. Testing whether the result was positive really means consulting the condition codes set by the subtract instruction. Note that we don't have a single flag that indicates a positive result. You might think that the sign flag does that, and it will be false for a positive result, but also for a 0 result. We'll need some combination of the flags to signal a result strictly greater than 0. That combination is shown here. This condition is true whenever 2 things are true. First, the result was not 0, and second, the sign and overflow flags have the same value. Let's think about why this says that the subtraction resulted in a positive number. First, the result was non-zero. That's pretty clear. But second, the result either was non-negative with no overflow or negative with overflow. The first part of that is straightforward. But why do we allow a result that is negative with overflow? Well, if the result was negative with overflow, that means that the arithmetic result of the computation was actually positive, but overflowed into the negative range. That's a case you might not have thought of, but ISA designers have to consider all such corner cases. Jump if greater and the other conditional jump instructions of the x86 allow for testing a variety of conditions expressed as logical formulas over the condition code flags. Typically, these involve comparisons between a result and 0. But what if you need to compare two arbitrary values, rather than compare a single value to 0? The compiler will reduce this problem to the problem of comparing against 0. For example, x is greater than y if and only if x minus y is greater than 0, and x is greater than or equal to y if and only if x minus y is greater than 0 or x minus y equals 0. We often implement this in assembly using a compare or CMP instruction. For example, consider this C code fragment to return the maximum of two values. The compiler might generate the code shown here, where x is in register EDI and y is in register ESI. By convention, the value is returned in EAX. The compare statement computes y minus x, but doesn't store the result. It only sets the flags. Using the JGE, or jump if greater or equal instruction, we branch to appropriate code to return either x or y. By the way, the condition for JGE is shown here. Either the result is non-negative without overflow or negative with overflow. In this case, it's okay for the result to be 0. Finally, let's consider the x86 test statement. Test xy computes the bitwise AND of its two arguments. Like CMP, it doesn't store the result, but only sets the flags. For example, suppose we wish to see whether the value x stored in register RBX is even. This will be true only if the least significant bit of x is 0. We could check this in assembly with the code shown here. The test statement will compute the bitwise AND of x with a constant 1. This will yield a result of 0 if and only if the least significant bit of x is a 0. The result isn't stored, but the 0 flag is set, which allows us to branch to the appropriate code to handle the even and odd cases. There's a lot more to learn about the use of condition codes in the x86, but this is a good start.